h of x, h of p, less than log m. Makes sense. If I have a die with 8 sides, equally probable, then there are 8 possible outcomes. It takes 3 bits to describe it. And the entropy, indeed, of the distribution 1/8, 1/8, uniform is 3 bits. So we also know that the entropy is always non-negative for discrete random variables. And so we have the desired result. We also have it by inspection with equality if and only if P is uniform. That's nice. By the way, there was another way to prove this. So H is minus summation Pi log Pi. Now you want to maximize H over P. So you form the functional J of P as minus summation Pi log Pi plus the Lagrange multiplier lambda times summation Pi, because the P's have to sum to 1. Then take the partial derivative. And that's why I have natural log here. For the ith term, all the terms with index other than I, this is a dummy here, here's the I, will not depend on Pi. And the term that does just becomes minus log Pi minus Pi over Pi, and then plus lambda. And we'll set this equal to 0. This, of course, is 1. And you get log Pi as a constant, or Pi equals 2 to the c, well, in this case, e to the c. But the summation of Pi equals 1, so you bring the constraint in. And so, therefore, e to the c has to be 1 over m, because this sum is m times e to the c. All right. So that way you get, therefore, P star is equal to 1 over m, 1 over m. Then you plug that back in the entropy, and you find out, indeed, you get the entropy of the uniform, which is log m. So that's another way to do it. Problem: if you do it this way, you have to argue that you have a maximum instead of a minimum, because you've only set the gradient equal to 0. All right, so you do that. And then you want to argue that it's unique. And to do that, you might want to find the matrix of second derivative. And show that it's non-negative definite and strictly positive definite, and you're on your way, and now you proved essentially what we proved here using Jensen's inequality. Or actually, since we've already proved that, we just used D is non-negative. Great. Okay, now for one of the key inequalities. Okay, H will be concave, but we want to know for what value of P is H maximized. Oh, yes, good. Right. Once we've done this with the Lagrange multipliers, we can appeal to the fact that H was concave, strictly concave, and therefore has a unique maximum. Right. But notice we're begging the proof of Jensen's inequality when we do that. So, yeah. By the way, it's really nice that mutual information is zero if and only if you have independence. As you all know, the correlation between two random, or the correlation coefficient, essentially for zero mean random variables, is the expected value of x times y over the product of the standard deviations. And you can have uncorrelated random variables that aren't independent. For example, if x and y lie on a circle, then you have a lot of dependence, but the correlation coefficient is zero. So there's a sense, and it shouldn't be too surprising, that the mutual information gets to the bottom of things, that it's zero if and only if you have independence. Now, here's one of the key facts. Information doesn't hurt. And that is that the entropy of x given the observation of y is less than or equal to the entropy of x. Again, with equality if and only if x and y are independent. This says your uncertainty about x is decreased by the observation y. Now, yes and no. If you recall, h of x given y is the conditional entropy of x given the observation y equals little y, averaged over y. So, for some values of y, you may get actually an increase in entropy and some decrease, but on the average you get a decrease in the entropy. Now, that's nice. You can imagine the prosecutor's office for something. They're about to go to trial, and they get information. Oop, A's looking guilty. You get more information. Y2, he's looking guiltier. Y3, aha, he's guilty beyond a reasonable doubt. We can take the person to trial. And then you get another piece of evidence that makes it, I don't want to hear anymore. You get some more evidence that throws the likelihood down below the 0.95 probability of guilt. This is where prosecutors get in trouble because they sometimes forget to pursue that extra information and to reveal it to the defense. All right, the proof is nothing more than this. I of xy is equal to h of x minus h of x given y. And I is greater than or equal to 0, so therefore, bringing that over, you get the desired result. Would equal if and only if x, y independent. By the way, here's a fun example, not very information theoretic, where you can get a huge piece of evidence that indicates guilt. And you have another piece of evidence, a huge piece of evidence that indicates guilt. But you wish you didn't have them both. All right, here, someone robs a 7-Eleven. 1 minute later in the alley next to the 7-Eleven, and the robber is described as a one-armed man. And 1 minute later in the alley, you find a person missing his left arm. So he's booked and taken to jail because he meets the description. And then you have to admit that's rare, and so, and he's very near the crime. The problem is there's one more piece of evidence. He's missing his right arm also. So the likelihood ratio blasts back down again. I was recently talking with a recent PhD who's now at Princeton, and it's fun. And we're trying to come to grips of who's the best weather predictor. What does the weatherman say? He says there's 50% chance of rain tomorrow. And that's what, indeed, if you look at the almanac or records of the past, that's how often it rains in January, half the time. So you say, well, what is he? But there's another weather predictor, a true wizard. And he says there's 100% probability. He's talking street talk here. There's 100% probability that it'll rain tomorrow with probability 50%. What's the difference between these two guys? One is just says it's going to rain with probability 50%. The other says she's 100% sure it's going to rain with probability 50%. Okay. The best we can come up with is it's the invulnerability to further information. For example, if we're going to flip a coin tomorrow, I can make the wizard statement and say, there's 100% probability that it's going to rain tomorrow with probability 50%. In other words, I've squeezed all of the information I can out of the weather prediction problem, and I'm left with a fair coin flip. Whereas the other guy might say, oh, probability it's going to rain tomorrow is 50%. And then you say, wait a minute, it's raining in Los Angeles. He said 60%. And then there's a storm coming from the north. He says 70%. You know, he can be all over the place. He is not invulnerable to further information. He can have a substantial reduction here over the entropy. And so he's a poorer weather predictor. It just happened on that day they both made the same statement. But one you can believe more than the other, even though they're saying the same thing. Okay, you know, I should have really proved that h of p is concave. So I will